Right. I was asked three questions related to elliptic curve cryptography on a forum, and I thought I would just outline uh, really the background to these questions. So the three questions I was asked is why is NG safe? So as we'll find, NG is the public key. And why is it that we cannot determine n even though we have g? The second question uh, I was asked is how do we compute n g? Do we have to add the point n times? That's obviously going to be highly efficient. Or can we actually calculate it straight away? So I'll try to explain how we can compute our public key in an efficient way. And the third one, and it's very interesting, is how do we use elliptic curve cryptography to actually encrypt? So we see elliptic curve cryptography used in digital signing and with key exchange. So that's two of the strong areas that it's involved with. But how can we actually use it to encrypt data from Bob to Alice? Okay, so I'm going to try and explain these different questions in a simple way. So let's start at the beginning with elliptic curve cryptography. Okay, so with elliptic curve cryptography, what we have is that we have y squared is equal to x cubed plus ax plus b. And we also have the mod of a prime number. So the curve that we use within Bitcoin is this. So A is 0 and B is 7. And then we take a mod P. The prime number itself is a large prime number, uh, something like uh, for a different curve, it's 2 to the power of 255 minus 19. We have 256 bits for our prime number, which defines the basic security of our curve. Okay, so this is the basic equation that we have. And now we need to look at how our elliptic curve is created. So the curve that we get looks a little bit like this. We pick a base point G on the curve, and then we determine our private key. In this case, we'll define it as n. N has, say, 256 bits. So we take G and then we keep adding G to get 2G, 3G, 4G, and so on. In the end, we end up with a point which is NG. This is an XY point. This becomes our public key. And this public key, uh, we should not be able to determine the value of N, even though we have G. And because n is a 256-bit value, then it would take too long to brute force all of the values because we have 2 to the power of 256 different values of n. And if we started to compute, it would take too long for us to actually determine the correct value of n from there. To give you some idea, 72 bits is a typical size of a crackable value for what's called the entropy or the key size as possible within a reasonable amount of time to crack 72 bits. 128 bits is much more difficult. Double, double, double until we get to 128. If we go from 128 to 256, it is almost impossible to be able to determine the right value if this is a truly random number that we've actually selected from there. And the way that we perform our elliptic curve cryptography is that we take a point and then we add another point to give us the resulting point. We can also take the same point and double it. So the two basic operations that we have are add two points together or double a point. And the point that we get as a result, it is not possible for us to be able to reverse that back to the original point, or within our current computational resources, if we take our 2 points together and create a new point on the elliptic curve, it is not possible for us to reverse that back to find the 2 points that created that. Same again, if we've used a doubling operation, it is not possible to be able to find that value of p, even though we have the value of r. Okay, so this is where the strength of elliptic curve comes in. We have this adding operation and the doubling operation. I'll show you a demonstration of that in a little minute. So hopefully you've seen that it's extremely difficult to be able to find that value of n, even though you have the ng point, because there are just too many points to look for. So the second thing is, how do we compute the public key, the value of ng? Do we have to take this random value and add? That would take too long because we have a 256-bit value. It would be it would take an almost infinite amount of time to be able to compute that value. So what we do is that we use the Montgomery ladder method to do this. And this is a time constant method. So no matter the value of n that we select, it will take the same amount of time to compute the value of ng. In cryptography, we can use what's called a timing attack. And with the timing attack, we can measure the amount of time it's taking to do the computation, and we can often work out what the key is or some secret thing in it. So with the Montgomery method, we either perform an add or a double operation. So in elliptic curve, all we need to do is to add 2 points together or double the points. No other operation is required. So let's take a sample of 71. It's a small value, but we'll make it simple so that you can see the basic principle. So 71 in binary is 1000 111. It's a 1, a 2, a 4, and 64 gives us 71. So what we do is that we take each bit at a time. We're going to take each bit one at a time, and the number of operations that we'll do is the number of bits that we have in our value. So normally that will be 256 operations that we'll have, but we've only got 7 bits here. So what we do is that we have a running uh, uh, total of the doubling points. So wherever we see a 1, we want to create an add operation. If we see a 0, we don't add, but we double at the point. And in the end, we'll add up all the add operations. And we keep a running tally of where we are with the point. Remember, what we're trying to do is to get n, which is 71, times g. Okay, so we're going to start off with a base point, g, and then we're going to end up with 71g in an efficient way. So we start off with a 1, so a 1 is true, so we'll take the g and it's 1g. So that's an add operation. Start off with 0 and we do an add to give us g. And then we'll double our point now to get to 2g. That's a 2 times the point. And then the next operation, we also have a 1, so we'll take the 2g running double and we'll add that. So now we have 3g and we double the point here to give us 4g. It's a 1, so we'll take the 4g, 4 times the point up here through this doubling operation. We're doubling all the time, and we'll add that on there. We'll double the point to give us 8g. Now we get a 0, so we don't add anything, but we'll double the point here. We have a 0 here, don't add, we'll double the point to give us 32g. Here, again, we don't add, but we'll take 64g. Now we have a 1, so we take 64g here. 64 add additions of the g point gives us that point there. We will now take all of that. 64 plus 4 plus 2 plus 1 is 71g. So in this way, we go through the operation, and all we need is to keep a running tally of the point related to the bit pattern that we have, and we just double. So for the 256 bit, we will have 256 bits all the time of our random value, and we'll go through 256 operations. And we must always do that, because if we miss off the zeros at the end, then that gives a clue to an adversary that we're using zeros. So no matter what happens, we will go through all of the bits one at a time and work out the key. But now we have the public key, and the public key is now done not for the number of additions of n, but through this Montgomery ladder. Okay, so I think hopefully that illustrates how we create the public key efficiently, and also why it's not possible for Eve to determine the value of n because it's so large, even though we have the point ng. Okay, so now let's look at the third question that was posed. How do we use this in terms of encryption? Well, it's not like RSA where we can encrypt and decrypt. We take the message to the power of E and then take the cipher to the power of D. That doesn't quite work with elliptic curve cryptography. What we do is that we do the same thing that we do in the elliptic curve Diffie-Hellman method, kinda, to generate the key. What we do is that we pick our symmetric key encryption, and we will use elliptic curve methods to generate the symmetric key. So we might use AES or another encryption method. But what we want to do is for Bob and Alice to agree on the key that we're going to use purely by sending Bob's public key. Okay, so how does Alice get an encrypted message to Bob using elliptic curve cryptography? So we use ECCIES, and this is a way for us to use symmetric key encryption, which is very efficient anyway, much more efficient than using public key encryption. The problem that we have with elliptic curve is that we only have 256 bits in our prime number. So the range of messages would be so small that we couldn't encrypt a file, say, because we only have a few bytes to be able to create our message space. So the first thing, so let's say that Bob creates a value of B. That's his private key. And now his public key, he takes the point on the elliptic curve, as we've just saw, G, and then through 256 operations of the double or add, he ends up with his public key of BG. He sends that over to Alice in some way. She'll find a way to get a trusted version of that key. Now, Alice creates a random number for each message that she wants to encrypt for Bob. Okay, so she then on the same curve with the G value works out a point RG. Okay, so then she takes Bob's public key and multiplies RBG, the random value times the B value times the G value. She obviously can't work out what the G value is, but she'll create a new point on the elliptic curve equal to that. She then sticks that into a key derivation function with the point here, and we'll end up with, say, a 256-bit AES key. She then takes that key and encrypts the message that she has to Bob. But at the same time, she sends Bob the point RG. So we have the cipher here, and she'll also send RG, which is the point on the elliptic curve with the random value. Okay, and then all Bob has to do now is take that value and multiply it by B. So he gets RBG or BRG, or they're the same thing. He sticks it through the same key derivation function and ends up with a 256-bit AES key, and that's the same as the key that she has used here. It's random, so every single time we encrypt, we'll get a new random. So we're not using Alice's private key here, as we would do with something like the elliptic curve Diffie-Hellman method. In the end, every single message that she sends to Bob will have a new random value. And Bob will check that to make sure that every single time it's a different point on the elliptic curve that we get. So there's a randomization in there, and then they'll end up with the same key. So in this case, we're using symmetric key for our encryption, but we're using public key to be able to generate that key. So this is a very efficient way. Nobody ever gets to see Bob's private key in this case. Okay, so I hope that's explained that. So I'll just show you a couple of demos here. So here is our elliptic curve point adding. If you're interested, this is the equations here. It's a very simple operation where we get 2p is just achieved through this simple operation that we have here. And then we take a point and add the point and get another point on the elliptic curve. So the thing about the elliptic curve is that we take one point and another point, we'll usually always get another point on the elliptic curve, and we can check for that. So that's why we start with a point and then we keep going on, and every single time we'll get a new point on it. Okay, in terms of the parameters, so this is the Bitcoin curve, 0, 7. Here's the G value. This is the point on the curve for Bitcoin. And there's the prime number there. Okay, we can look at other ones. A very common curve is 25519. And we can see here, there's the A value, the B value. There's the elliptic curve point 9 is the X value for the base point and elliptic curve, and there's the prime number, which is 202 to the power of 255 minus 19 in there. So that gives us each our different curves. We can get an even bigger curve if we want here with P519. From that, that's minus 3, and there's the big V value, there's the G value, and there's the very big prime number that we use for P512. When it comes to uh, the encryption, so here's an example here, and we can use a different curve if we want. But here what we're seeing is Bob's private key here. That's the B value. Bob's public key here, which is a point. We then create the cipher. There's a random value in there. So the cipher that goes across is here. And then in the end, we'll generate the same encryption key and to be able to decrypt there. So if you're interested, here's an example with the with AES encryption in there. So we can see here we're picking a random number. That's going to be Bob's private key that we're picking, scalar value, 255-bit. We then create a public key based on the value that we've selected, B in this case, and the G point to give us our public key point. We can then feed that in and then create the encryption from them. Okay, so I hope that's kind of explained the three different areas. Okay, thanks.